Okay, so we are recording. Picking up where we left off last time, we were almost done with section 1.2. Yeah, so there was really only one last little bit to show. It's not really on the exercises that I recall. Kind of academic, but this is a good thing to know. This is fair game material for exams, and that is how, if you have a line in R3, how would you make what I'm going to loosely call an equation, right? Now keep in mind the role that an equation plays when you're talking about a line in R2 is that it's a point tester, right? Well, we can't really make an equation for a line in R3. That would give us a surface, not a curve. But what is going to play the role of a point tester, right? If I want to have a point tester, like an equation kind of was doing in a different context, how do we do that? So the big idea is to take your line in R3, parameterized, so the point generator, in other words, and I'm going to start off by making the seemingly useless observation that a test for whether your point is on a line is, well, does there exist some value of t for which this formula generates your point? Right? Now that's, how would I know if there is a value of t? That's not particularly immediately helpful. I'm sorry, I forgot to explain notation on this. This symbol right here, kind of a backwards capital E, that's just a mathematician's shorthand notation for there exists, or there is, something along those lines. And this notation here is another little shorthand for such that or so that, something along those lines. Okay, so seemingly a useless observation. Here's the key idea. The key idea is to recall that this is actually three separate equations. Right? It's a vector equation. That means that each of the corresponding coordinate equations must be true. In each of these three equations, solve for t. Easy little bit of algebra. If you solve for t in the first equation, you get this. Second equation, you get that. Third equation, you get that. So, does there exist a value of t? Turns into actually a much simpler question. And that is, does there exist a value of t that's equal to all three of these things? And if you think about it for a quick moment, a single value of t cannot equal to three different things unless those three things are all equal to each other. Right? And so that is our final, what we call the symmetric equations, and what plays the role of a point tester for our line in R3, and that is I need these three things that t has to equal to all be equal to each other so that it's possible for t to equal to all of them. And a nice, satisfying little punchline there. So anyway, called the symmetric equations, handy thing to know about, and moving along. So that finishes 1.2. On to 1.3. Reminder, in this course, there's just a tremendous amount of material. Tough choices. Y'all are going to have to fill in the gaps on the things that I don't talk about in class. And things that I think y'all have already seen before, not going to make the cut, right, for class time. So much of this stuff I'm not going to talk about at all, because you should already know it from linear algebra. So make sure to read through section 1.3. Make sure there aren't any things in there that you haven't seen before. But you know the formula for the dot product. You will recall, I'm sure, that this is the model for a very important idea in linear algebra called inner products. And I think that's worthy of mention. It's just a powerful, very powerful idea for whatever it might be worth to persuade you on this. One of the big ideas in image compression actually fundamentally uses inner products as one of the primary sort of tools for that. So I think that's pretty cool. Okay. If I can get the where's my button? Why is my stylus already out of battery? Come on. Surely not. Oh, I'm sorry, my stylus is already out of charge. I just plug this in. It'll charge up in a few minutes. Yeah, that's what it was. Okay. All right. Okay, so I do have one additional terminology thing that I want to talk about, and that is these two words, perpendicular and orthogonal. A lot of books will be a little bit fast and loose about the distinction between these. I'm going to try to explain why I think it's important to distinguish these words from each other. I think you already know what I'm talking about. They basically both mean that the vectors kind of make a right angle with each other. Certainly that's what perpendicular means. And orthogonal, a lot of people think, is just a synonym for perpendicular. Not quite right, I think. And certainly it's a missed opportunity. So here's the situation that we have. We have a geometric idea when you're referring to non-zero vectors. There's this idea that two vectors define two different directions. And when you have two different directions, you can talk about the angle between those two directions. This is all geometry talk, directions and angles, right? All geometric. Okay. Now, there's a related idea, which is a purely algebraic idea, and that is that sometimes when you have two vectors, the dot product is zero. And again, y'all know already, these are very closely related, right? The difference is here, this algebraic idea, aside from being, again, totally different context of an idea, right? One's geometric, one's algebraic. But also, this algebraic idea about dot product being zero makes perfect sense when either or both of the vectors is zero. Whereas the idea of the angle between them and that being a right angle, that doesn't make sense when either of the vectors is zero. So we have two importantly distinct ideas, and with a lot of overlap. But you can't talk about how these ideas are different if you use the same word to describe each of them. Right? You can't discuss the differences between things if you can't even distinguish between them. So I think it just makes loads of sense to use one word to describe one of these ideas and the other word to describe the other of these ideas. Right? You got two words, you got two ideas, let's pair them up. So I try, and I've developed some bad habits over decades. I wasn't always as precise as I'm trying to be now, right? But I will try to always use the word orthogonal if I'm talking about dot product being zero, and I will try to always use the word perpendicular when I'm talking about something geometric, something about there being a right angle between two directions. And I urge you to try to stick to this as well. Okay. All righty. A couple other things we need to talk about. This is a very quick one here. If you have a non-zero vector, thus defining a direction, and if you want to find the unique unit vector that points in the same direction, here's the handy-dandy, super convenient little formula right there. All you have to do is take the vector itself, divide it by its magnitude. Game over, we win. Real simple formula. Again, you've probably seen this, but make sure that you know it. If you have not seen it before, it'd be a good exercise to think through why is it that this does what we want it to do? Why does this give us that unique unit vector? Okay. And by the way, this is a very, very useful trick. Needing a unit vector pointing in the right direction, and thus needing this formula comes up quite a bit in this course. Okay. All right, moving along. Component. So a component is something that we talk about when we have a vector, some direction and magnitude, whatever, and a corresponding direction indicated by some other vector. And I find myself wanting to talk about not how much does W point in the direction that it's pointing, but how much does it point in the direction that the other vector is pointing. So an easy example of this comes from football. If the football starts the play at that location and then ends at that location, I mean, you don't always get tackled straight downfield from where you started, right? Sometimes they run off to the left or off to the right, whatever. How many yards did you gain? Well, it's not the magnitude of this vector, right? It's all that matters is how many yards did you make it in the downfield direction, right? So, an easy, hopefully relatable example of what we're talking about here. So, what we will call this is component. Component is that scalar right there. Now, very importantly, it can be negative, so I have to be cautious. I have to do my best to restrain myself from calling this a distance. Can't say distance. Distance is an intrinsically positive thing, right? This doesn't have to be positive. You can get sacked in football and have a negative yardage gain, right? Said differently, if this W vector is pointing back this way, like so, right, then the component should be thought of as being negative. That said, I predict I'm going to mess this up at some point, so please forgive me. And if I describe a component as being a distance, you know what I meant. But again, I'm going to do my best, and likewise, I urge you all to do your best on that as well. Okay, pausing real quick. How are we doing on the idea? Geometrically, is this satisfying? Okay, the algebra on this is actually pretty straightforward. So we can, first of all, let me erase, and then I'll point out that we have ourselves a right triangle here, and we can write down the trig of that right triangle, cosine, and all that, right? So, boom, easy freebie. We realize that the component that we're trying to find a formula for is right there, and I can just solve for it. And then I can rewrite like this, doing just a quick little bit of algebra with one little clever trick in it, and that is to notice that here, where I have legally, seemingly pointlessly, but legally multiplied and divided by the same thing, the purpose of which was to allow me to rewrite all of this as the dot product, using, again, that standard old formula about dot products. So, nice punchline. Let's see, erasing again. So if you want to know the component of one vector in the direction of another, here's a nice little formula to plug and chug into. Okay. Now, here's a twist. Different way to write this formula. Same formula. Let's see here. That formula, morally equivalent to this formula. All I've done to distinguish these formulas is I've taken what I see here, V divided by magnitude of V, and I've just noticed that that is exactly the unit vector that points in the relevant direction. Right, and this leads to what I think is a really nice little bit of intuition for how to think about components, arguably a nice intuition for how to think about dot products, is right here in this formula, just encoded in this formula, and that is that components are dot products with unit vectors. Right, it's tempting, an overstatement, but it's tempting to think, oh, dot products are components. And not so, right? Dot products specifically are only components when the direction vector in question is a unit vector. You do have to be careful about that. But nevertheless, it's a very strong, intuitive interpretation of dot products by way of components. Everybody okay with this? Questions? No? Right. Cool. Okay, related idea. Projections. Not the same thing, but commonly confused. Oh, and also a terminology problem. A lot of people say projection when they mean component, sometimes even vice versa. There's just not really a perfect consistency on the choice of words involved with these things. So in this class, though, projection is going to be something different from component as follows. The component is the scalar. Again, you're going to want to call it distance, right? But you know what? It's how far in that direction. It's a scalar. The projection is the vector. You might say component represents the scalar amount that W points in the direction of V. A projection is the vector part of W pointing in the direction of V. One's a scalar, one's a vector. Everybody see the difference? Okay. We can connect them pretty straightforward. Notice that the projection that we're trying to find a formula for, we know what direction it points. We know what its, I'm going to say magnitude. Again, forgive me. It's not positive necessarily. Doesn't have to be. But we know what we want to multiply that unit vector direction by. And so making this observation, the vector that we're interested in here, this projection, very easily written by noticing again that the unit vector is something that we know how to compute. And again, the scalar, how much we multiply that unit vector by, is also something that we know how to compute. So very handy little formula. It's handy. It's also, though, and I think importantly, easy to understand. Right? This isn't something that you should memorize per se. This is something that you should understand the reasoning for, and then you can't but help to have it remembered because you understand the idea. Right? So I'm a big fan of this formula. Let me circle specifically. This is the way that I like to understand projections because I understand it. It's immediately. There's no algebra between me and this result. It's just this is component times unit vector direction. There's nothing to it. Okay, now that said, our book prefers a different take on this. Our book takes this formula, same formula. It rewrites the unit vector using our formula from the previous page for how to find the unique unit vector pointing in a given direction, right? And then multiplies, collects terms, blah, 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 and you end up with this alternative formula for projection right there. Now we have a pro-con situation. Which formula do we like better? Do we like, actually let me erase the stuff there. Do we like this formula up here, which is arguably a shorter formula, or this formula down here, which is, I'm going to say more explicit. You give me a V and a W, this tells you where to plug what in and turn the crank. Right? So which is better? They both have their purposes. They have their moments. This formula down here is good if what you're going to do is do a bunch of arithmetic. And if you're going to be actually plugging and chugging with arithmetic, yeah, sure, this is the best formula. Let me remind you that's not really what this course is about, right? I mean, yeah, sure, there's going to be a little arithmetic here and there. Mostly this is a course about ideas, and I think the ideas are more visible and relatable here. So I encourage you to take this point of view instead of this point of view. For whatever it might be worth, when I see students use these formulas on exams, I see this formula at the bottom oopsed quite a bit. Students will, they'll do like W.V divided by W.W. or something like that. Or maybe if the vectors aren't called V and W, the point is they get it just a little bit wrong in any of several different ways. I've never seen this one done wrong. So again, this is one of the results of focusing more on ideas and less on plugging and chugging. Yes.
So the top one is like it has to be a unit vector, right? But the
Yeah.
bottom is B doesn't have to be a unit vector to be anything.
Well, yeah, I mean, either formula will allow you to compute the projection even if V is not a unit vector. It's just that in order to use this formula up here, if V is not a unit vector, you have to first compute U. But yeah, totally. Yep. Okay. All right. Moving along. Last little thing, real quick. We're gonna mostly skip over this business about. I didn't quite get that to fit. This business about how you can use vector algebra to prove certain facts about plane geometry. There's some nice examples in the book. There's at least one exercise on the homework where you're going to use those ideas. Again, tough choices, classroom, contact time, we don't have enough. I think this is a pretty straight read, right? So make sure to read those examples as preparation for doing those exercises. And it's a really valuable little tool. It's something that you just don't have at your disposal when you're doing high school geometry. And you'll notice in the examples that some pretty neat little proofs that are much easier using vector algebra. Okay. All right. So that finishes 1.3. Moving on to 1.4. There is a bunch I'm going to say about 1.4. I feel like you've probably seen cross product before, but there's a lot of really important ideas about how cross product relates to other things. Geometric interpretations, there's just a lot to it. So I'm going to spend a fair amount of time talking about cross product. We won't finish it today. That said, there are some tough choices that I've had to make, and I've had to accept just due to realities being what they are, that I don't have time to talk about the proofs in this section. That are in the notes. Now, they're in the notes, and you can read them. By the way, I think they're very instructive. I think there's a lot of good intuition to be had from looking at how those proofs connect ideas to other ideas. And keep in mind, that's what this course is all about, right? So it always makes me sad that I can't talk about those. But you're not responsible for the proofs. You are responsible for the ideas and the results. Okay. All right. Starting with the first idea. Sorry, got ahead of myself again. I should point out there are different ways to approach the ideas in this section. It seems to me like every textbook I look at does them in a different order, makes sort of a different sort of collection of connections to establish the ideas. I have a preferred order in which I like to present these ideas. My preference is based on what I think makes the ideas most geometrically intuitive. That's my goal. The book presents these ideas in a very different order. And the order that Kali uses for the ideas is a very good one, and it makes a lot of sense, and it has some nice advantages. But I do think that it's more rigor-oriented. It's very algebraic. There are parts of it that are extremely opaque and unsatisfying. And yes, it's more rigorous, but I don't think you're going to like it as much. So for your consideration, please look at both, right? But I think you'll like mine. I think you'll find mine more satisfying. So, we'll see. Okay, so I want to start off talking about what I mean by a geometric interpretation of order in a list of vectors. And so first of all, here's a list of vectors. I emphasize this is not a set of vectors. This is a list of vectors. The distinction being that a list has an order to it. Right? All lists are ordered. So there is one that is specifically first. There is one that is specifically second. Whereas if you just have a set, there's no particular order on the set. Okay, so the idea is this. If I have the first vector, if I think of that specifically as being first, and the second vector, I think of that specifically as being second, notice that the ordering in the list from A to B is what you might want to call counterclockwise. This being the two vectors A and B. I mean, this is the first one, that's the second one. That takes us in a counterclockwise direction. Everybody see that? Okay, now, if I were to look at a different pair of vectors, A and B, if that is what A is, and if that is what B is, now still, A first, B second, that list goes clockwise. Again, it's just how the vectors are sitting down in the plane. So, in some sense, whenever you have a list of vectors, generically anyway, maybe not quite always, but you'd think going from the first to the second, so you're either going to rotate counterclockwise or you're going to rotate clockwise. Now, of course, there are some cases where that doesn't happen. For example, in this case, there's no rotating at all. They're pointing in the same direction. This list, the list A comma B, for those vectors A and B, is neither clockwise nor counterclockwise. And analogously, what if A is 0? What if B is 0? What if they're both 0? So the various different versions that don't fit into the clockwise, counterclockwise, and what you're going to quickly notice is that in all of those cases, the list is dependent, linearly dependent. Flashback to Math219. Everybody on board? Okay. Now, this idea of clockwise, counterclockwise has some really nice properties. They're pretty easy to persuade you of if you reflect a counterclockwise list over a line. The reflected images will be clockwise. So reflecting switches the order, you might say. It's pretty simple picture, I think. Here's another property, pretty believable, I think, and that is that if you trade, if you put B where A was and A where B was, right, then the result is that what had been a counterclockwise list turns into a clockwise list. Well, again, I think that's pretty believable. Just look at the picture, pretty satisfying. I hope that hope you buy it. And then lastly, I think this is a nice property to observe. If you have a counterclockwise list, such as I have here, and if you then take the entire picture, this entire picture, right, rotate both of the vectors. Oh gosh, let's see here. Rotate both of the vectors like so. The resulting list of rotated vectors still counterclockwise. Again, I think this is pretty easy. I mean, if I were to take that clock off the wall and hold it up here, and then you observe that the second hand is going in a clockwise order, right? If I were to take the clock and rotate the clock, the second hand would still be going clockwise, right? It doesn't make any difference. Rotating doesn't change the direction of a rotation. Okay. All right. Everybody happy? Yeah. Yes?
I don't really get what trading positions in the list changes order means. Like, what if
yeah, so
linearly dependent? What would trading positions?
Oh, well, if it's linearly dependent, then yeah, it doesn't. Then changing the order will still be linearly dependent. What I mean by changing the order is if you have one that's counterclockwise, and then you trade positions. Let me do this. If you have a list that's counterclockwise, and if you trade positions by taking what had been the first and making it the second, and taking what had been the second and making it the first, that will turn counterclockwise into clockwise. Yeah.
So this property only applies to the counterclockwise, clockwise?
Yeah, that's right. Yeah, it dependence stays as dependence. Yeah, right. Everybody happy? Okay. All right. Okay, so that was an easy concept. Clockwise, counterclockwise, very everyday, right? And that's not news to anybody, I hope. Here, though, is what I'm going to call the three-dimensional version of clockwise, counterclockwise. And this is something that you might not have seen before, and it's certainly not in sort of everyday use, in society. So, things just get a little bit weirder. Again, this is going to be a way of making a geometric association to an ordered list in a way that's going to have analogous properties. This time, 3 vectors in space instead of 2 vectors in the plane. Okay, so here's how this works. I'm just going to have to hand gesture. Sorry for those watching the recording. Here's what a right-handed list would look like. Again, assuming that A is first, B is second, C is third. And just to be clear on that, A is first, B is second, and C now is third. So we're going to use the human right hand to do this. It has to be the right hand, by the way. The right hand, it matters. Left hand is not the same. Importantly different. Right hand only. Here's how you do it. Point your index finger in the direction of the first vector. Now, when you do this, it is required that your index finger stay parallel to your palm. Right? So nothing like this. No, that's not fair. Right? Index finger parallel to your palm. Now, you can turn your hand however you like, right? But your index finger has to be parallel to your palm. Okay, now, next. Your middle finger needs to point in the direction of the second vector. Now, my finger doesn't bend that way, but keep in mind, I can turn around the axis of my index finger however I like, and so making the appropriate choice. Now I've got my middle finger in the direction of the second vector. Everybody good? By the way, no fair doing this kind of nonsense, right? You can't stretch your finger backwards. The middle finger has to bend the direction the middle fingers want to bend. Okay. Now here's the thing. These first 2 vectors, A and B, define a plane. The thumb of your right hand points on one side of that plane. Right? In this case, given this plane, there's what you might call the above side and the below side, right? But in particular, whichever side your thumb points on, if the third vector points on the same side of the plane as your thumb, then we call that a right-handed order, or right-handed list. That make sense? All right, so that's a kind of a weird rule. You can probably guess what left-handed means. Same story, just use your left hand. And notice what I've got down here with A now being way over there, first vector way over there, second vector now over here, third vector still the same. This is no longer right-handed. In fact, I have to do it like this, right? If I'm going to point my index finger in the direction of A, the first vector, notice in order to get my middle finger to work out, again, I can't cheat, right? This isn't allowed, right? I have to turn my hand like this in order to allow my middle finger to go in the direction of the second vector, B. Now notice my thumb points down. My thumb points opposite of the direction of C. So it is not right-handed, but it's easily seen to be left-handed. Everybody happy? So it's kind of like clockwise, counterclockwise. Generically, that C vector is gonna, you would think, in pretty much all cases, I mean, it's gonna either be on the same side or the opposite side as your appropriate hand. But of course, it could be that this will crash and burn in any of various different ways. So for example, the third vector could be parallel to the plane instead of on one side or the other. Or it could be the zero vector, or A could be the zero vector, or all of them could be the zero. There's various annoying little cases, but of course all of those fit again into this wonderfully convenient little category of linear dependent. Yeah? Okay. All right. And again, this behaves just like clockwise, counterclockwise. Right and left hands are mirror images of each other. Right? If you trade two of the vectors' positions, so if I put A where B was, and if I put B where A was, trading positions like that will turn a right-handed list into a left-handed list. So, for example, I claim that ABC, this trio here, this list, A first, B second, C third, right-handed. But this list, having switched those positions, B first, A second, C third, is a left-handed list. Everybody good with that? And again, how you rotate, as long as you rotate all the vectors the same way, right-handed stays right-handed, left-handed stays left-handed. This is a pretty easy thing to see again. If this is my demonstration that a given list is right-handed, if I rotate all the vectors the same way, this is still my right hand. It's still a right-handed list. Does that make sense to everybody? Yeah.
I had a question on the first property.
Yeah.
When you put like the A prime, B prime, does that mean anything like mathematically?
Oh, I just mean no. I mean it's not a standard notation. This is just the notation that I'm using to represent reflections.
Okay.
So like if I were to take this vector and think about how it reflects through that plane, this is what its mirror image reflection would look like, and I'm just using a prime to distinguish them. That's all. Yeah. Is that cool? Yeah. Okay, so it's. I think this is a really nice observation. This whole business about right-handed and left-handed gives geometric meaning to an ordered list in a way that satisfies analogous properties with respect to mirror images and trading positions and rotating the whole picture exactly like clockwise, counterclockwise. So this is what I like to call a three-dimensional version of clockwise and counterclockwise. Side note, there is a fourth property that's useful to have, and that is that if you cycle a list, by which I mean if you take the first vector in your list and put it at the end, like so, this is what I call cycling. That preserves order. And a pretty good little intuition for this is, so if you watch my hand here, this motion right here, notice as I have my hand arranged here, I'm pointing in the direction of these three vectors A, B, C. As I have my hand arranged here, I am pointing my fingers in the direction of A, B, C, just different ones in different orders. And geometrically, cycling looks like this little motion right here. And of course, this is my right hand, and this is still my right hand. And so that's why it preserves order. Okay. Geometric intuition. Okay. Let's talk about some theorems that relate to right-handedness, left-handedness, and clockwise, counterclockwise. You may have seen these from your linear algebra class, depending on which course you took. I'm going to review them here because I think they're important, starting with the two-dimensional theorem. There's a fair amount of setup in this theorem. I'm going to start with a list from which I'm going to generate a matrix, from which I'm going to generate a transformation, from which I'm going to generate a parallelogram that will relate back to the initial list. None of which actually makes any statements. That's just stuff that I want to talk about in the conclusion of the theorem, but I do need to kind of talk through what is all this stuff that I will be talking about in the theorem. So starting with the list, again, whatever vector is first, whatever vector is second, what we're going to do to that list is we're going to make a matrix. Let's see here. Let me erase that. We're going to make a matrix by making the first vector the first column and the second vector the second column. Now, I just made that up, right? But again, I'm going to make these things and I'm going to talk about them later. Okay, so that's how I'm going to make a matrix from a list. Given a matrix, there is a corresponding linear transformation from last week, right? Given a linear transformation, let's see here. Notice if I were to take the unit square, and if I were to look at the first standard basis vector, which of course is one of the edges of my unit square there. Let's see here if I can. This thing's messing up there we go. Okay, actually this is probably charged again. Let's try this. Yeah, good. We're back in business. Okay. If I look at that first standard basis vector and ask what is the image of that first standard basis vector, well, we have a rule for this. If you want to know what the image of a standard basis vector is, it's the corresponding column of the matrix. Now, we talked about this on first day of class, right? It's a reminder of one of the important fundamental properties of the relationships between matrices and linear transformations. The columns are the images of the standard basis vectors. So the image of E1, namely the image of that first edge, is this first column, which of course is the first vector in the list. Now, analogously, if I look at the second vector here, the second standard basis vector, its image is going to be the second column, which of course is the second vector from our original list. So, keeping in mind, from this original list, we made a matrix, which gave us a linear transformation, which now has given us a parallelogram, and conveniently, the edge vectors of the parallelogram are the original list of vectors. Now again, I haven't proved anything yet. I'm just making stuff about which I'm going to make some statements. Does everybody understand the process by which I've generated these objects? Everybody good with the objects? Okay. All right, so here's the first important statement. And I got to clean up the mess here. Very first important statement is there is a shocking relationship between the matrix and the parallelogram, namely, as I have written here, the absolute value of the determinant of the matrix will always be the same as the area of the parallelogram. That is I think, a really shocking fact. Let me explain why I think this is shocking. For one thing, this is an algebraic object, right? Determinant is it's a formula. Area is a geometric thing. It's part of a picture, right? So these things seem to be different kinds of critters, and it's always unexpected when when things that come from really different places happen to always be the same. It's a real eyebrow raiser. The second reason, though, is if you look at the formula for how you compute determinant, absolute value of determinant, this is multiply and add and subtract. It's four-function arithmetic, right? There's no far out fancy operations happening here. I'm multiplying and adding. Whereas if I were to take a high school approach to how to compute this area right here, I'd need to compute this length. That involves a square root. That's a little weird. It would involve, I would need to drop a perpendicular and compute the height. That would involve computing trigonometry for this angle. That's pretty weird, right? Trig and square roots all over the place in this calculation, only 3-function arithmetic in this calculation. Shocking that this would work out. Almost doesn't seem like it could possibly work, but it does. Okay, neat fact. Second neat fact is that the sign of the determinant, that's SIGN, plus or minus, whether the determinant is plus or minus, tells you about the ordering of this list. So keep in mind, we had this original list of vectors, A and B. A first, B second. And the geometric feature of whether this is clockwise or counterclockwise is visible in the algebraic, just the sign of the determinant of the resulting matrix. And again, really unexpected, seemingly really different kinds of ideas, but this indicates that. And specifically as follows, the correspondence is that if the determinant is positive, negative, or 0, that corresponds to the list being counterclockwise, clockwise, or dependent. And that's a really cool fact. Last thing is the sign of the determinant also tells us something about this linear transformation, and this linear transformation right here. Oh gosh, which, by the way, let's talk about what's happening inside of this linear transformation. Just, based on what's in the picture here. Based on what's in the picture, it looks like maybe things were kind of rotated, and then there was kind of a shearing motion, and then maybe a magnification, or something like that. But notice, it doesn't appear that anything got flipped upside down, right? But some linear transformations do. For example, if I were to switch these vectors, if I were to say that the image of E1 was this, let's suppose that's what A was, and let's suppose that this was my B, namely that was my image of E2. Notice what we have here is that what was originally green to blue counterclockwise has become now in its images green to blue clockwise. And no amount of stretching inside of T, no amount of shearing, magnifying, whatever, right? None of that's going to turn counterclockwise into clockwise. Only a flip. Only if you flip it upside down will that happen, right? And that is the foot in the door to make this observation here, that about the transformation, whether or not the transformation here has a reflection inside of it somewhere, is again indicated by the sign of the determinant. So positive means there's no reflection. Negative means there is a reflection, such as how I have it drawn in here now with my modified drawing. And then, of course, there's always the possibility that something anomalous and annoying could happen. Determinant could be 0, and that means that, well, something weird has happened. Something's been squished. To say it in linear algebra language, the column space has dimension less than or equal to 1. You might say the matrix is singular. Something weird's going on, right? Something anomalous. So again, interesting information about the algebraic properties of the determinant, and geometric information about, this time, the linear transformation. So, shocking fact, and let's see here real quick. Let's see, how much time do we have? I've got 15 seconds. That'll do. Exactly the same theorem is true in 3 dimensions. It's exactly what you think. It's right and left-handed instead of counterclockwise, clockwise. It's 3 vectors instead of 2. It's a parallelepiped instead of a parallelogram. It's volume instead of area, right? But if you just take the theorem on the previous page that we just talked through and make your guess as to what the 3-dimensional version ought to be, you'll be right. It's exactly morally the same idea. So that'll do for today, and see y'all later. Have a good one. We'll pick up here on Friday.